Hello students! So consider the collection of all possible maps from V to W. What does it mean to add two maps? Well, we should know what that means because hopefully we've looked at some examples of the vector space of maps and then we know how to add maps and scalar multiply maps. But just to quickly review, if T and U are maps from V to W, doesn't matter what we call these vector spaces, what you can do is you can say, hey, I'm going to define T plus U of V to just be, hey, T of V plus U of V. So I have a new map called T plus U, which is just, hey, the sum of T of V and the sum of U of V. Okay, and similarly, I can define lambda T of V to just be lambda of T of V. Now, if T and U are linear, so are these. Okay, so how do we show something's linear? Well, we show that we can split up sums and pull out scalars. So let's first show this. T plus U is linear. Proof. Okay, so we're assuming all of this. We're assuming that T and U are linear. I want to show that T plus U is linear. So what might I want to show? Well, let's take T plus U of vectors V plus W. It might be a little confusing because V and W are both in V, right? Because that's the stuff that goes inside the function, but I could call it V plus U. I think it's okay. I mean, U would have its own problem. We already have a U. I could call it A plus B. Let's just leave it like this. So what is this defined to be? This, by definition, is T of V plus W plus U of V plus W, because that's how we find out where T plus U takes things. Okay, but now T is linear, and so is U. Okay, well now let's regroup. And what is this? Well, this is the definition of T plus U of V. And this is the definition of T plus U of W. So that completes the proof. Oh no, I want to show it's linear. That completes the first part of the proof. I'm doing both parts here. So let's move on to the next part. But as an exercise, make sure you can go through these steps and see what's used at each point. Next part. Suppose we have T plus U of lambda V. Okay, well by definition, this is T of lambda V plus U of lambda V, which is equal to what? Well, T is linear, and U is linear. So now what can I do? Well, I can pull out a lambda. This is taking place where? In W. So this is lambda of T of V plus U of V, which is equal to, well, what's this? This is the definition of T plus U of V. So that proves that T plus U is a linear map. Now, next, we might want to show that is a linear map. So let's show lambda T is linear. Proof. By the way, this is a nice short one. You might want to pause and see if you can do this on your own. Okay, we'll assume you did that. That's the map. Now, what's this defined to be? This is defined to be lambda times T of V plus W, which is equal to, because t is linear, t of v plus t of w. So now I can distribute in w and what's that equal to? Well, that's equal to, since this is lambda t of v and this is lambda t of w, that's just going to be, we're done. There's actually nothing more to do there. That was the last step. There is no other step, because we showed that lambda t of v plus w is lambda t of v plus lambda t of w. So, I mean, what did we do here? Well, we used the definition of lambda t, right? Then we used the fact that t is linear. That gave us this. Then we distributed that lambda. And then we just used the definition of lambda t again. Okay, that's just part of it. In order to complete the proof, we now want to show that we can pull out scalars. Now, I do not want to use lambda in the same proof twice to mean the same exact thing. So let's use, I don't know, alpha for our scalar. So let's take lambda t of alpha v. Okay, well this by definition, by the definition of lambda t, is this. And t is linear, so this is lambda times alpha of t of v. Now, of course, we can just group that like that if we want. That's not quite what we want, right? We don't want to leave this like that, so that's not really going to help us unless what we want to do is this. And you know, with our, it's not associativity, but it's the compatibility law of vector spaces, because it's not associativity, it's not three of the same thing. I can switch this, and I don't have to write the parenthesis anywhere, because I can group like this, or I can group like that. I'm not going to write that out, but we are using it. And then, what do we have here? We have alpha times lambda t of v, which by definition is this. Boom. We are done with the proof. So, if t and u happen to be maps from v to w, and they are both linear, then their sum is linear, and any scalar multiple of the map is also going to create a new linear map for us. So that's a nice way to create new linear maps from existing ones.